When looking at a set of data, explain how to determine if that set of data is normally distributed. Now, we have to be very careful about what we're going to say here. Remember, if a set of data is normally distributed, then when I look at a histogram of it, it should be mound-shaped and symmetric. It should follow the 68, 95, 99.7 rule. However, if instead I turn this set of data into a normal probability plot, then the normal probability plot of that data will be approximately linear if the distribution is normal. However, when I say that here, I have to be specific. I have to say something to the effect of the normal probability plot for this set of data should be approximately linear. And that's a perfectly reasonable explanation to say how I can tell a set of data is normal. However, I can't say this, right? Ignore that. Some of you wrote this. It is linear if normal. And I go, what? What's linear? It, meaning the data? No. This data is it's univariate. There's only one variable. So it doesn't make sense to say that the data is linear because I can't make a graph, I can't make a scatter plot out of univariate data. So what do you mean is linear if the distribution is normal? Well, you mean the normal probability plot is linear if the distribution is normal. The data itself is not linear. It's mound-shaped and symmetric, and it follows the empirical rule. It's the normal probability plot that is linear. So be very careful when you try to explain the reasoning behind how you can tell whether something is normal. Be specific. What do you mean by it? You mean the normal probability plot, or do you mean the data itself? Because that data clearly can't be linear because it's only a single variable. It's univariate data, not bivariate data. Question 12. You sample from a population that has a mean of 100 and a standard deviation of 15 for the variable you're interested in. Can you find the probability that your sample mean is smaller than 95 if your sample size is 9? Well, notice, it doesn't say anything up here about the population being normally distributed. So therefore, I can't find this probability because my sample size is too small. So the answer is no. The population is not given to be normal, so we need a large sample size. However, the sample size is only 9. N needs to be greater than 25 for a large sample. And remember, that's where the central limit theorem kicks in and saves us. If our sample size is bigger than 25, then we don't care about the population being non-normal. But if we don't know anything about the population other than its mean and its standard deviation, we don't know the shape of the distribution of the population, then we need a large sample size, and 9 is not large enough. Number 13, a dishwasher costs $800. The dishwasher will fail and need to be replaced within 5 years only 10% of the time. The manufacturer offers as an extended warranty to replace the dishwasher if it fails within the first 5 years for a cost of $50. Should you buy the warranty? Use expected value in your argument. So we actually had to construct the expected value. So we think about what can happen here. Either the dishwasher fails or it does not fail. Well, it fails 10% of the time. It does not fail 90% of the time. Well, it's all about this $50. I have to spend this $50, right? Well, if I spend the $50 and the dishwasher does not fail, well, then what happens to me? What's my X? Well, I lose $50. I'm out that $50. I've spent it, and I don't get anything back for it. But if the dishwasher fails, Then they replaced the dishwasher, which means I won this $800. But I had to spend the 50 to get it. So I didn't really win 800. I really won 750. So if it fails, I won 750. If it does not fail, then I lost 50. So now we just need to find the expected value. So that just means find the mean. So we multiply these together. 10 times 750, that's 75. 90%, 0.9, times negative 50, that's negative 45. And we add those up. And that adds up to $30. Notice that it's positive. That means the expected value for this, for you, is positive $30, which means you're going to make $30 in the long run if you take the plan. So if you were to repeat this process over and over and do it many, many times, you would have a $30 expected value. Now, clearly, you're either going to be out 50 or you're going to gain 750. But it's this long-run probability, this long-run expected value that we're interested in. So if many, many, many people do it, on average, you're going to come out $30 ahead. Therefore, should you buy the warranty? Yes. The expected value for you is positive. Number 14, if the distribution of grades on SAT math tests is normal with a mean of 500 and a standard deviation of 100, find the probability that a randomly selected test score greater than 550 points. So I know I'm looking at a normal curve. The center of the distribution is 500. The standard deviation is 100. So there's one standard deviation that gets me out to 600. Well, our score is only, 550, which is right about there. So we need to find the probability that a random selected test is greater than 550 points. So we're going to find what's the probability that x is greater than 550. That's the same as the probability that our z-score is greater than, what's the z-score for that, right? So we're going to find our z-score. It's going to be 550 minus 500 divided by 100. So that's 50 divided by 100, which is 0.5. So we're going to say, what's the probability that our z-score is bigger than 0.5? So that's this area out here. So then we're going to go distribution, normal CDF, from 0.5 up to infinity, and paste. And I get roughly 31%. So this is equal to 0.308. So that's all they asked for, 30.8%. And the last one, if the distribution of grades on the SAT math test is normal, mean of 500, standard deviation of 100, find the probability of selecting a random sample of 40 tests that average greater than 550 points. Notice, it sounds like the same problem, but we're doing an average of 40 tests, right? So a single observation is roughly 31% likely to be bigger than 550 points. But for 40 tests to have an average that's bigger than 550 points, that's a lot harder to do, right? That's going to be because our standard deviation will be much, much smaller. So we have to find again our z-score. Our z-score is going to be 550 minus 500, just like it was before, divided by the standard deviation. But now we're doing the standard deviation of the sampling distribution, so that's going to be 100 divided by the square root of 40. So we're going to go 550 minus 500, which is 50, divided by 100 over the square root of 40. And we get 3.16. So that means this distribution looks more like this now, right? So here's 500. No longer is one standard deviation equal to 100 points. So one standard deviation is going to be 100 divided by the square root of 40. One standard deviation is now only 15.8 points. So this is 515.8. This is what, 531.6. And this is 547.4. See, so we're way out here at 550. That's shockingly unlikely. So finding that probability, we're going to go distribution, normal CDF, from 3.16 up to infinity, gives us a highly unlikely event. So the probability that our z-score is as big as 3.16 is approximately 0.00079. So would you be surprised if you pulled a sample of 40 tests and their average was as high as 550? Yes.